Well, hello everybody. I'm Tony and I'm responsible for starting AIMSEC, and there you see me working in South Africa with some learners. I think they were grade 6 or 7 learners in the local primary school in Muizenberg, where AIMSEC is based. Caroline?
Hello. I'm Caroline. I am the founder of Bubbly Maths, and my passion is that every child on earth will love learning and enjoy mathematics. How do I reach every child? By reaching their teachers and their parents. So that's why I'm working with Tony to reach as many of you as possible and help you make maths interesting and engaging for your learners.
Mary?
Good afternoon, everyone. I'm Mary Ochieng, an alumni of one of the AIMSEC programs and a teacher of mathematics. And I just enjoy supporting teachers to be able to give their learners a good experience in mathematics classrooms.
And when Mary was a student with AIMSEC, she was a school teacher, and she then went on and did a PhD after doing our 2-year course, and now she's a lecturer at university in Kenya. Okay, so the program for today. So it's quite simple, really. We're just adding 2 numbers and seeing what the answer is, or using that in sort of all sorts of different ways, the same idea. We're going to be doing a little bit on the geometry of circles and triangles as well. So we hope that if you use these ideas, that it will today improve your skills, knowledge and understanding, but it will, moreover, when you use these ideas in the classroom, they will improve the skills, knowledge and understanding of your learners. So the first one statement is addition and subtraction, simply adding and subtracting numbers. And to understand that the inverse, if you've done an operation like 3 + 6 = 9, and you know the 6 and the 9, you need to get the 3 by subtraction, and they're inverse operations. And we're going to use the same idea with fractions, not just whole numbers, but with fractions and exponents. We're then up to secondary now, factorizing quadratic expressions. Then we're going to move on to simple circle geometry, solving simultaneous equations, similar and congruent triangles, and parallelograms. There's lots today. Now, we like to describe lifelong learning as a spiral where we keep hearing again about ideas that we know about or learnt about, but learning more as we come back to them later on this same spiral of learning. And the spiral you see there is meant to depict the school spiral, starting in a reception class, or some countries it's called, well, even starting at nursery, preschool, and then moving up to lower primary, upper primary, lower secondary, upper secondary. And then the top is like a springboard, like a diving board in a swimming pool, if you like, where you're launched into adult life we've had good teachers with all this knowledge and skills that you're going to need at that stage, and the ability to go on learning. So these are the stages in school. And so what we're going to do here is unusually making a list from the bottom, because we're starting with an activity that you can do with everybody, including small children. And as we go up the spiral there, we're going to do a game that we call Checkit, with different sets of numbers and different rules, with fractions, with word puzzles, with algebra, with exponents, lots of variations on this one game or puzzle. And then we're going to go on to something we call Polycircles, which is like a necklace of circles. touching circles, and then that's going to lead to solving simultaneous equations. And the last section is on the midpoints of triangles and some pure and some analytic geometry there. So we have a rich feast of mathematics for you this afternoon.
We're all going to participate as we make comments in the chat. We'll be asking you to make guesses, and maybe, you know, things, we'll be giving you things to think about.
The Checkit game, there's two main features that we're going to be using, two main tools, let's say. Both of them have a huge range of usefulness. Now, this version of Checkit is perfect for early years. It's also great for learners who struggle. So they might be 16, but they have learning difficulties. So it's still useful at any age with people with learning difficulties, but it's a great introduction. Now, Checkit's a fantastic game, very versatile. And the idea is you've got this board, you can do it on a piece of paper, you can do it on a board. And I've actually got a version of it. I'm using lentils. You can use whatever you want. You can use any kind of flat counters. And what we've got is we've got 2 lentils. As you can see, we've got 5 in the next box down. Then you've got 3 at the top bottom right. You've got 6 bottom left. And so very, very easy. I've hand drawn this frame. You don't have to print out anything. And so might have taken it in turns to place counters, or you can present this as we're doing with you now. You can present this to your group of learners as you see this. So what you've got to do when you play the game, you play it, and the learners play together, and they've got to make sure each other doesn't make a mistake. For example, and you only get points if you don't make a mistake. You might get points taken away. If you don't, you can play it as a game. But right now, what we'd like you to do is work out how many lentils or checkers you're going to put in box A and box C. How many lentils can you, by deduction, you don't have to play it by deduction, but you're grown-ups. I'm going to play it this way with you. With early years, you can actually be more direct a little bit more. But for you, how many lentils or counters should I be putting in box A and box B?
Just adding here.
A is 8. This gives you the opportunity to you can either put the counters in a random way, or you can make patterns. And making patterns, of course, can help with instant number recognition. B equals 9. That's essentially the way Checkit works. Mary.
And now we're going to do Checkit with 2-digit numbers. So again, we want to fill in the boxes, the rectangles, and we want to fill in the rectangle a number that is the sum of the numbers at the vertices. So again, just put in the chat what you think those numbers would be. And Caroline is also has also put that up for us. She's also going to fill in those numbers for us, but let's see what you have in the chat. Okay, Antoinette says the left box. Okay, Antoinette says the left box should have 144. Caroline has put that down for us. Bottom box, 154. And 187 on the right box. It's 143, the sum of 88 and 55. Yeah. Thank you. Thank you.
Well done, everyone.
So for the next one, again, we are adding, but now we have 3-digit numbers. And this time we have one of the vertices, one of the ellipses not having a figure. So again, your guesses of what we should have in each of the two boxes and what should be in this vertex here. Let me call it a vertex because we have a triangular kind of shape. Again, the number in the middle edges should be the total of the numbers at the vertices. So Mashabela says the top one is 234. So
And
Caroline,
Mashabela had to do a subtraction to get that answer. And that shows that you have an inverse there. It's an inverse operation. Subtraction of 333 minus 99 gives you 234.
And then let's see, in the chat we have C. Someone is saying C is 165 in the chat, and the left rectangle is 300. Yes. Thank you. Yeah, so this was slightly different from the other one where we were only looking at sums, and as Tony has pointed out, for us to get what Mashabela got, the 234, they needed to do an inverse operation, the inverse of addition, which is subtraction. Okay, thank you. And the next one, so you can see how we can do this with, we started off with counters. Caroline was using lentils. Then we went 2-digit numbers, and now we've done 3-digit numbers, and we've had a shape where we even did an inverse operation. And so in the next slide, we're going to look at how we can do Checkit, but with fractions this time. So if we have fractions, and this would be a nice way, a nice thing to do with your learners, especially if they're doing addition, and subtraction of fractions. This would be a nice activity to do with them. So again, please put in the chat what you think should be in the rectangles. So Pam says the left, 14/15, the bottom, 11/10, and see something else in the chat. 5/6.
And I think this is a lovely way to play a game with fractions and get the practice you need to become skilled expert at adding fractions, but in an enjoyable way. For the children won't see it like drill and practice. It'll be a game, but they'll be getting the practice that they need.
So the idea with this slide is that you can use this slide for the method, the Checkit game. As Tony just said, it's a game. They're practicing, they're getting better at their skills, and it's completely up to you how you use it. You can keep it super simple with the counters. You can make it, as you'll see later on, we're going to do algebra with it. You can do it the showboard format where everyone has their own little Checkit on their show me card, or simply the answers. So you can say, okay, what belongs in the bottom left-hand vertex? You can give them numbers or letters, and everyone can show you the answers. You can make it a puzzle. You can make it a game between two people. You can make it a challenge where everyone has to create their own game, which incidentally you will be doing during the break in not so many minutes. It's a very versatile activity that you can do as a starter many times throughout the school year, and you can literally use it for the activity that for the topic that you're working on at any given time. Have you anything to add, Tony?
Well, Caroline has explained that there are so many ways that you can use this. It's once the children see this frame, they'll understand the general idea of what they're going to be doing with it, but you can vary it in so many ways, as Caroline has said, with different numbers, different operations, and sometimes revealing 3, sometimes even giving them a little bit more help. And with just revealing 4 of them and getting them to find the other 2 answers. Once they get used to it, you'll agree the rules at the start, and then they can play it in pairs around the room in your class. Practice whatever it is that that lesson is going to be about. There's a list there of all sorts of different things they might be using it for, including things like factorizing algebraic expressions in secondary school. So, and we're going to move on to using it, the same idea in geometry. So it's a lovely idea. Okay, so now we're going to move on to, we call this making it up as you go. I mean, basically starting with a blank. And the idea here is everybody's got to be really creative, because what we're going to do is to fill up these boxes with the, I think we'll start off with whole numbers, and Mary and I are going to play the game to demonstrate it first of all. And we can put any numbers we like in the boxes. However, there must be an answer possible. I mean, so we can't make it impossible for our opponent to put a number in. We can't do that. And if we do, without intending, make it impossible, then we're going to lose a point. So you see, supposing we play this, Mary and I play it, that we're going to put numbers in such a way, just as we have been doing in some of the earlier ones, that what goes in the middle of the edges is the sum or total of the numbers that are put at the vertices. And we can actually put Mary and I will put numbers into different boxes, and we'll choose which box, and we'll choose our number. And so we'll each put in 3 numbers. And if, when we check it, everything's correct, we'll each get a point, or 3 points if we've agreed to 3 points. But if we make any mistakes, then we lose a point. Mary, what would you like to do? We'll do it with whole numbers. So shall we set a limit on the numbers? What do you think?
We could start off with the single digit numbers. Do we want to?
That's a bit easy. Let's make it 2-digit numbers. What do you think?
Okay, no problem.
Okay, 2-digit numbers.
All right.
Now, so we're going to take it in turns to fill in one of the boxes, always making sure, as I've just said, that it's possible to complete the set of 6 entries. And then, if challenged, a player must show they can find numbers to complete all 6 entries. And we check each entry before moving on to the next one. And players score a point if they make 3 correct entries and lose a point if they make a mistake. Or if you decide the rules is 3 points, that's fine. I think the thing to bear in mind as teachers is that you are able to make different rules for on different occasions when you play this sort of game. Okay, and you're going to record this, Caroline?
Mm-hmm.
Yes, I'm ready, standing by.
Right. So
no pressure, Mary.
All right. Especially we're doing this for the first time. We didn't rehearse this, so it's okay.
And I did a very good job of saying I'll record it instead of having to work it all out.
Okay.
Mary, you put the first number in then, and we've got the boxes A, B, C, D, E, F. So you just say which box.
Okay, I want to put 88 in box B.
Okay. I'm going to put 79 in box E.
Hmm. Oh, okay. All right. I'm going to put 26 in box A.
And when you're playing with your learners, you have to make sure, especially if you spot a problem, they have to be able to explain how they are actually going to be able to complete the Checkit board. You have to know what they're doing. They can't just guess.
Yeah. So if you're challenged, then you must be able to explain how you would finish all 6 entries. I'm going to put 62 in box D, Mary. That was easy.
You said you're going to put what? 60?
62 in box D.
All right. Okay. Okay. If you put 62 in box D, then I'm going to put 17 in box F.
That's fine. I don't see any problem there. That's going to work because I can now put in box C 43.
Mm-hmm.
Yeah, it works for me.
Okay, so now we've done a demonstration, so I think we should start all over again, but this time everybody here will be able to contribute, and we'll watch the chat, and what we'd like you to suggest is, anybody can suggest anything, that a box, tell us the letter for which box it is and the number you want to put in it, okay? And so perhaps if you've got pencil and paper, draw your own triangle and keep a record of what's happening. Caroline will keep a record, and we hope we can go through this with this is actually not, we could play it in 2 teams. We could play it as my team and Mary's team. Perhaps we'll do that. Okay, so will you decide, please, whether you're going to be in my team or Mary's team? Okay, and we will take it alternately, and Mary's team will start first. So if you're in Mary's team, then please would you make a suggestion as any number you like. Mary, shall we do this with, shall we make it a little bit more challenging and do it with 3-digit numbers this time? After all, we're teachers, we're not little children, so let's make it more challenging and make this with 3-digit numbers. Okay, so if you've decided to be in Mary's team, would you like to give the first number?
Oh, so Pam's made some observations.
Chiffy,
oh, great.
Somebody, Chiffy, has said 300 in A.
Yeah, 300 in A, right? 300 in A. Here we go. Thank you very much, Chiffy.
So somebody in my team?
In box
Sorry,
B.
Box B, what goes in box B?
I want to put 34.
34
341. Yeah, 341.
341 in box B, and that's Tony's team. Okay, yeah. Thank you.
Pam suggested D 41, and Fanel is also saying in box D put 41.
Antoinette says 175 in E.
175 in E. That's Tony's team.
We have 2 boxes left. Pam says 134 in F.
134 in F.
Antoinette says 166 in C.
Is that correct? Are we good with that?
Is it? I'm not
Yeah.
sure. No, we've got an answer now from
4, 3, 4.
from Makongelo. From Makongelo.
Yeah, and we had an announcement as well. We had I don't know if it's Noxolo or John coming on as well to say, yeah, 4, 3, 4, very loud and clear. Thank you. Pam has explained the number that she wrote in C, and that is that she was following a different thread. She was assuming a different number. So what she's saying is, if they'd written 123 in C, you'd have had a negative number in F. So
that's interesting. Yes,
exactly. It's a very rich activity.
Oh,
and these are the
fantastic.
kind of observations that your learners will also make, because
Yes.
it's such a rich activity that several of them will make suggestions, and you can have these discussions, and they'll be engaged in doing arithmetic or whatever you're working with, instead of just having to do them as rote activities.
Well, I love it, Pam, because what we've got here is a sort of a natural way of finding, well, there doesn't seem to be a solution here, or maybe that's wrong, and then actually seeing that you're dealing with integers, negative numbers. So it's a great way to introduce integers, isn't it? Then you can talk about temperatures inside freezers. I love it. So so you can see how really versatile this is. And we've got some more surprises for you. Exponents.
Now, this was a big surprise for me, Tony. I was not expecting this activity. And when I realized we're not going to be adding, we're not going to be multiplying, we're actually going to find factors. Not only that, we're going to be looking at the greatest common divisor between those 3 vertices. So we're keeping it as simple as possible. All you have to do, so it's not much, is to work out the common divisors, the greatest common divisors between each of the 2 vertices. So we've got 3 boxes, and see if you can work it out. And I've got the easy job. All I have to do is write down what you say and make sure that it is right.
So you could talk with your learners here about the number at the top is actually 60, but what you're doing is breaking the number 60 down into its prime factors, which is 2 squared times 3 times 5. And then the one on the bottom right is 147, which is 3 times 49, or 3 times 7 squared. And the one on the bottom left is it's 2 times 3 squared times 7. So it's 18 times 7. So what's that? 18 times 20, and subtract 2. Well, I'll leave you to do that. You can see I'm hesitating to do the mental arithmetic. What a coward I am. Okay. Okay.
I
So
find it very hard to do it on the spot, and it's
yes, well, so now what we want you to do is to take, we started with something a little bit easier. We've just started with the exponents, and what we want you to do is to find the common factors and put it in the boxes, the rectangles. What are the common factors of these 3 numbers? And don't bother with the big numbers that we've just talked about. Just look at the factors, and that's the way to find the common factors or common divisors.
We do actually want them in the form of prime numbers. So
As well.
that's an extra challenge for you, Pam. We want the
Yes.
prime numbers.
Yes, yes. You can write those numbers as products of primes, or you can write them as Pam did as the numbers, the greatest common factor or greatest common divisor of the two numbers on that edge at the vertices. The left rectangle is 3. The right rectangle is
it's the other way
it's the
around.
bottom
The
one,
other way
actually.
around. It's the other way around. It's all right. It's left and right. I think Nobom has it. It's just it's just said left instead of right, which is hard to see sometimes, especially on Zoom.
Oh, okay. Yes, I'm sorry about that. So as Caroline's written it, it's 3 times 2 or 2 times 3 on the left. And it's on the bottom, 7 is a common factor, and so is 3. And you've given us 3 times 7, 21 on the bottom. And on the right, what have you got there on the right? You've got 3
on the right,
as a
it's just
factor.
3. Yeah,
yes,
just 3. That's it.
Yes, and this is a hugely important idea in mathematics, this idea of prime decomposition. It's sometimes called decomposition of whole numbers into a product of prime numbers. So this is really, I think this is a lovely activity. And there's no reason why you shouldn't also use the middle boxes for common multiples. See, we've used them for common divisors here, but we could also use it for common multiples. What's the lowest common multiple of the 2 at the edge, the 2 numbers at the vertices, and put that in the boxes? So with the one frame, as you see it on the screen, there's another variation that you can play right away. And it's a way for learners to appreciate that these 2 ideas, lowest common multiple and greatest common divisors, are different, or greatest common factors are different, but to see how this plays out when you look at this scheme of the triangle or Checkit scheme. And of course, lowest common multiple is so important when it comes to adding fractions. It's exactly what you need to put on the bottom when you add fractions, isn't it? Okay, so Mary, we're going to move on to something that's a little bit different now. It's not even mathematics.
Yeah, and I think this is really, for a lot of teachers who teach, especially in the primary schools, they often teach more than one subject. And so, yeah, you could be teaching maths and also teaching English. And so this could be a way of, a way of, also just, building up the vocabulary of your learners and maybe even their spelling as they play a game like this. So you can do Checkit with words. And we have, I want you just to consider, the rule here is that the adjacent words must have 2 common letters. And so there must be at least 1 common letter in all 3 words on each edge. So in this case, you can see for the tiger at the vertex and goat, the word in the middle here is goose. And you could do this with different words. You actually, just the same way that we played with Tony when we were doing the numbers, you could even do this with, children can come up with different words and just, going by the rules, be able to come up with, words where you have the word on the edge having at least 2 common letters with the 2 words at the vertices. So I know Tony had kind of gone to the next given out, but if you didn't see those, I just want you to tell us what you think would be in the places in the vertex that we have here, where we don't have a word.
Or if you did see them, Mary, how about a different word?
It would be nice if you had a different word, because
word, yeah.
there's lots of possibilities. And when I made this up, I thought of creatures, you know. Well, we've got a bird and an insect and 2 mammals there, but they're all creatures, you know. So you could make them creatures, or you could just use any words you like, you know, like table or tree or anything you like, even people's names. So here's a chance for you to be creative, for you to give different suggestions about filling this in. So you see there with tiger and goose, they have got G and E in common, and with ant and rat, they have got A and T in common, and tiger and rat, they've got R and T in common. But what we're suggesting, but for adjacent ones, the 2 to fill in, they only need to have one to make it easier. They only need to have 1 letter in common.
We have giant suggested.
Oh, I like that one. Oh, I like it. I like it. So it's giant on the bottom left, from Chiffy. Somebody got a suggestion if we put giant there, what we could put on the right. I love giant because that's probably another creature. Oh, rabbit, great, because rabbit has an R and a T in it.
R and a T, yes.
Okay, so that's 2 suggestions. Would somebody like to come up with some other words?
I can write outside the boxes. This is
Yes.
again a great activity for learners to do in pairs. And then you can compare, maybe you could give them all the same starter and then find out all the different words that people come up with. Rose.
Someone is suggesting rose.
Rose, would that be, where would that go? Here, rose would go here. Where the R is the same, is common. Goose.
Oh, rose would go where goose
good
is.
for the go. We got goose there. Got goose right there. That's one of our starter words, but I like it. What's good for the goose is good for the gander.
Well, you could actually have gander, you know, because on the bottom left, because gander would agree with G and R with tiger, and with gander.
Goose. The G would be common, and then the A and just the A to the right, and the G along the diagonal.
Oh, but we said we had to have 2 common letters.
I thought it was just 1.
Oh, okay. What it's adjacent words.
2 common letters in that case, no.
2 common letters, yes, for adjacent words, 2 common letters.
Okay.
On the edge, and then for all the 3 words, there must be at least 1 common letter.
So rabbit would work, but rose wouldn't.
Yeah.
But you can make different rules. You can make whatever rules suit the group of learners that you're working with. You can give a greater challenge once
but rose would go not where you put it, but it would go in. It could go in the bottom left as well, couldn't it? Because it would.
You wouldn't have 2 common ones here, though.
Rose.
S and E with goose, and
you got it here, but not here.
R and E with tiger. Oh, yes. Not along the bottom.
Yes.
Not along the bottom. Yes, that's right.
In fact, you haven't got anything on the bottom.
Actually, this is very good because if you're doing it in primary school, but it's quite fun for anybody, you also get some practice in spelling and thinking of spelling, don't you, as well?
And this is a legitimate maths activity as well, just purely from the point of view of using the same skills, especially using words.
And logical reasoning, of course, isn't it? That just shows you my 2 examples of goat and tadpole, and how you can, how you've got the common letters and they're put on the edges there. We're going to look at some algebra now. So Mary will tell us about this one.
Yes, and so we're still doing Checkit, but now we're doing this with algebra, and we're doing this with quadratic expressions. This is something that learners would meet somewhere around grade 10. Grade 10, I think about grade 10, they should, this is the point where one would be doing quadratic expressions. And so this is a good thing to do with learners, where you can play a game where they, when they're doing factorization of quadratic expressions, they can find common factors. So so in this case, for this particular one that we have up here, we have a quadratic expression in A and D and E, and we want each entry should be a quadratic expression. So, and there must be a common factor in all three expressions on each edge. So we want to find the missing expressions. So I just want us to think about this and think about what would be in part B. What is a common factor of the expression x squared minus 1 and the expression x squared plus 5x plus 4. And for F, we already have we already have E filled out. So then we need to think about what should be in F, and again, what should be in C.
Put an expression in B, so there's a common factor between A, B, and D. And actually, there's more than one answer. Noxala is saying that the common factor is x plus 1. So indeed, you could put x plus 1 in B, but that's not quadratic. So what we want you to do is to put in B a quadratic expression. I mean, x plus 1 is correct insofar as there is a common factor between A, B, and D, but we want let's say they've got to be, each entry is a quadratic expression.
I'm going to put the common factors in on the outside though, because that's useful information. Relevant, isn't it? If the learners put those in.
So you can be creative here because there's lots of possible answers for B.
Oh, Noxolo is saying, let me try again.
Okay.
Good.
So now we've got x squared minus 8x plus 7 for B.
Sure.
X squared minus 8x plus 7. So
That's for B, and I've got for F, I've got x squared minus x minus 2.
So the two expressions that we've got there, B is, what is it? It's x minus B, what the expression that's been suggested. Ah, yes. Well, I was struggling to find your common factors, Pam. You've corrected it. It's x minus 1 times x minus, what is it? X minus 7 times x plus 1. That's correct. X minus 7 times x plus 1 in B gives you a factor x plus 1 that's common to A, B, and D. Now, F has been suggested as x squared plus 4x plus 3, which is x plus 3 times x plus 1, which makes x plus 1 common along the bottom and common between A, C, and F. We need something for C, and Antoinette has given us x squared minus x minus 2 there.
That's for C, x squared minus x minus 2. So you can see you'd need lots of sheets to make sure that I'm writing all your answers down here, all the possibilities, and you can assess them, see if they're right, have all the learners assess them and figure out which ones are right. They might all be right. And what a rich activity this is.
It is, especially because there's so many possibilities, but then they just need to identify what is the common factor and, write out all these different quadratic expressions that would then meet the condition that A, B, and D have a common factor.
And of course, what I really like about this is that the learners can be creative. And it's a very good general principle that's to get learners to invent their own questions, to invent their own, in this case, game or puzzle, and to do it in algebra, with algebraic expressions, because actually they could be just adding the algebraic expressions. They don't need to be finding common factors. It could be much simpler. So let the learners invent their own games and then come to the board and involve the whole class in playing their game. And there's lots of possibilities. They can be very creative.
The other powerful thing here is it takes away a lot of the fear of making mistakes, because if everybody's making suggestions and everybody's making mistakes, then hopefully everybody will not feel that they'll be the odd one out if they make a mistake. So they might go ahead and brave an attempt, even if they think it might be wrong.
I think that's a very good point, and a general point about learning from the mistakes you make. Yeah, and as you saw this afternoon, we all made a few mistakes while we were trying to do that, and perfectly fine. We checked it as we went along, and that's the whole point of calling it Checkit. You have to keep checking as you go along. Okay, we're going to move.
Pam has just made a comment. It's interesting, as the others checking it have to factorize in order to check it. So it's an incentive to factorize because they want to check their colleagues' work rather than anything to do with the teacher, which makes it, oh, is it right, miss? Rather than, oh, you might be wrong, I'm going to check your work.
Yeah. Yeah, that's so relevant. That's so right. Yes, I agree with that.
So I've got here, Tony's got some examples there. So what we're doing here is we're simply creating a circle. I'm using household objects. I've got a plastic bowl. I've got a CD. I've got a box of wood filler. So we can start with 3. We can make a triangle with 3 things, with 3 circles. Now I'm going to add one. Question is, what polygon would you make if you joined all 3 centers of these circles? I'm going to add one. Again, what kind of polygon would you make by joining the centers? They're all touching, by the way. They're all definitely touching. What polygon would you make by joining all those? And look, I'm going to add, we're making a chain. They must be touching. They're not all touching each other, just along the outside, just along the chain. I've added a coin. It's all very, very simple household objects. And so any collection of discs or circles can be joined together to touch each other and make a polygon. If you join the centers of each of them, you will make a polygon. Now, given any polygon, can you always find circles that will touch each other in this chain, where every single circle will touch the circle adjacent to it when you where the center of the circle is the vertex of the polygon? That's the question. And look, the way Tony's written it is a much more concise question. Given any polygon, can you find circles with centers at the vertices of the polygon, with each circle just touching both its neighbors? So could you put on the comments whether you think you can always do this? You can always join circles together in a chain. Can you do the opposite way around and create a chain out of a polygon, any polygon? Go ahead, Tony.
I was going to say, logically in mathematics, a statement must be either true or false. And Caroline has demonstrated there that the statement is in red, and you've shown by my plates on the slide, is that with any collection of discs, they can be arranged to touch each other. But is the converse always true? So if you start off with the polygon, can you find circles with centers at the vertices of the polygon, with each circle just touching both its neighbors? Is that true always? And that's the question we're going to be thinking about. And this next slide shows you actually how it's linked. It's called the Polycircles puzzle, how it's linked to what we have been doing with Checkit. So if we
Sorry,
take...
Tony, can I just interrupt 1 second? Pam says, are we also talking about concave polygons?
No, we can. Well, sorry, yes, Pam, we can have them concave. Okay, they don't have to be convex. So on my pictures, I think they will be, but they actually don't have to be. And this can get more and more general, more and more sort of interesting in a way, complicated, I suppose. But if you start with a regular polygon, as you see there in blue, with the triangle, the square, and the regular pentagon, you can always do it because all the radii are just going to be equal. But once you don't have it regular, now look at the triangle on the right. It's actually a Checkit. It's exactly the same problem. You need R1 plus R3 to be 3. So the solution turns out that R1 is 1 and R3 is 2. You need R2 plus R3 to be 6. So we have 4 plus 2 equals 6 there. And R1 plus R2 is 5. We have R1 is 1, R2 is 4. So we have R1 is 1, R2 is 4, R3 is 2, and these are the Checkit solutions, and they give you the radii of those 3 circles. Our Polycircles is just an extension of Checkit, but there could be more than one solution for 3 circles, but only one if you're given the edge lengths. So supposing you're given the edge lengths 3, 5, and 6 here, then we put in the radii 1, 2, and 4. And if you check that up, you will see that 4 plus 1 is 5. So that's the number that goes at that vertex. In the center of the green circle, 1 plus 2 is 3. So that's the length of that edge, that distance, and the number that goes at the center or vertex of the triangle, the center of the blue circle. And 4 plus 2 is 6. So if that's the other edge length, then you put the number 6 at the vertex, which is at the center of the red circle. So if you start with any triangle, can you always find a solution? Well, let's think a bit more about that, shall we?
And a great way to do this is using GeoGebra with your learners. GeoGebra is free. It's a free open source tool that is great for mathematics. You can use it in algebra, geometry, in a lot of areas. And there's an online version that you don't need to download onto your computer or your phone. You can use it online as long as you have internet, but there's also a version that you can just download onto your computer. And you can use GeoGebra and just have the learners experiment. After they've found one solution, they can then experiment and see what happens when they change the shape and the size of the triangle. What happens each time that they change the shape of the triangle? Are they able to do the circles change correspondingly? But it's a great tool, not just for this, but even for other things. It's a great tool that you can use for exploring. And currently, it even allows you to create a classroom where if you are in a place where your learners all have access to a digital device, then you can actually create a classroom. And as your learners are exploring, you actually are able to monitor what every learner is doing. And you're able to then respond appropriately and, give them direction as they explore things like this. So I'll leave that to you to explore, and maybe it's something that we could maybe talk about maybe another time. But yeah.
Yes, and GeoGebra is extremely rich. It was invented by a young teacher quite a few years ago now, but there's a big community that use it, and it's open source. That means it's free, as Mary said, and people supply examples. So if you go to that website, geogebra.org, you will find hundreds of examples on all sorts of areas of maths, including statistics, and hundreds of examples for use with different ages. And learners are very quick to pick up using computers. Screens are much more sort of, they're more comfortable with screens often than us older people.
We are making a connection with the Polycircles and Checkit. So we're kind of back to Checkit, and we're going to connect it with algebra and all kinds of things, but also make geometry real. So you've got the example there, and the challenge is to solve the three equations being the length of each edge of the triangle that is formed by connecting the centers of the three connected circles. So find the radii and a solution for the triangle with edges. So you've got the formula there. Now we know that the edge lengths are 4, 6, and 8. So we've got the starter. We basically want to solve the three equations. So we're connecting all these things instead of going, hey, let's solve three equations, write three equations on the board and go. You've actually got a practical solution. You could use, say, a coin and show different things that are more or less the same proportions. So yes, we'd like to know, what is the length of A, B, and C? I assume you could actually put this into GeoGebra, Mary, and actually, would it help you actually come up with the answers? GeoGebra would do the job of the calculator.
GeoGebra can do a lot. I use it in class and I always feel like I'm barely scratching the surface. I'm just using it really minimally. It can do a lot. Yes, I can see Pam saying her summer homework, play around with GeoGebra.
Yeah, looks like Pam has got herself a project for the summer.
So now you have got some solutions there, and what you got is whole number solutions, by the way, and throughout this, most of these with whole numbers to start with, we've been having whole number solutions, but of course don't have to be whole numbers. But here we've given you something which involves whole numbers, and Caroline's going to continue with this. But I just wanted to say that in South Africa and in many countries, the children are taught to do two equations in two unknowns, and not three simultaneous equations in three unknowns. But with these particularly simple equations, they will find that they can actually, if they think about it a bit and help each other, they'll find a way to do it without being taught how to proceed when they have three equations. So over to you, Caroline.
Yeah, it's a great challenge to give them, because if they can do two, they can do three, as long as if you have three equations and three unknowns. So as we have had one answer in the comments. So take from equations 1 and 2, you know that A minus B equals 2. That gives you equation 4. Add equations 3 and 4 by doing that, you find that A equals B and C equals 3. A equals 5 and C equals 3. Therefore, you can substitute either one of those into 1 or 2, finding out that B is 1. So the radii are 1, 3, and 5 units. Thank you. We've had quite a few answers coming in there, as people have been working it out, 1, 3, and 5. Now, using the method above, you can actually find a generalization, a general formula, an algebraic way of saying it. So P minus Q plus R, and half of that is 1. If you do everything you've done, but you're not putting in numbers, you're just putting in letters, you will come up with P minus Q plus R. Half of that is one of them. P plus Q minus R, and half of that is another. And minus P plus Q plus R, half of that is another.
So what you're saying really is, Caroline, that if you have any triangle and the edge lengths are P, Q, and R, in the first example, they were 4, 6, and 8. But if the edges of your triangle are lengths P, Q, and R, you can always come up with the radii as with that solution.
And then to find equations for quadrilaterals, so for the equations, for the triangles, you need 3 unknowns and 3 equations. Extension for quadrilaterals, 4 equations, 4 unknowns. Pentagons, you need 5 equations, 5 unknowns, and keep it going. So again, you've got that lovely extension activity for those that finish the triangle and want to do some more. And then you've got the realization that, okay, this expands and it works as you add more edges to your polygons.
So now we've got some nice pictures up at the top right, a smaller picture. You'll see 4 red circles, all touching each other, polycircles, and you've got 12 green circles. Some of them are tiny, tiny circles, but you've got 12, 3 in each of the red circles. And that's a chain or a poly necklace of green circles there. Now the big picture shows you 4 red circles. So we're looking at a quadrilateral now. You see that in black. Your quadrilateral has its vertices at the centers, and you can see that all the red circles touch each other. And notice that the pairs of radii are tangents to that inscribed circle of the quadrilateral. So you have got from each of the centers of the big red circles, you draw 2 radii that are just tangent to the blue dotted circle. And of course, you have to teach in secondary that this theorem that from an external point, the tangents to a circle are the same length. And of course, that means they could be radii of a circle as they are in this picture. So this leads you to an interesting investigation. If you label the radii, these circles, as R1, R2, R3, and R4, what do you notice about the lengths of the 2 pairs of opposite edges of the quadrilateral? So here you've got R1 plus R2, and here you've got R2 plus R3 along this edge, and here you've got R3 plus R4 along that edge, and you've got along this edge, you've got R4 plus R1. And so what about the sum of that length, and can you see my cursor, and the length of the opposite edge of the quadrilateral? And what about the sum of this length and the opposite edge? And what you should find is that the sum of the lengths of the opposite edges, that length and that length, will be the same as the sum of the other pair, that length plus that length. Now, it popped up that this diagram of a rectangle, and that shows you that you can't always find a solution. So this picture here shows a rectangle, and it shows, I think, pretty clearly that if you try to do this with a rectangle, you can draw two circles that touch each other at the ends of the rectangle. They're fine, but they don't touch along the longer ends of the rectangle. So it works for a square. That's perfectly fine. You can start with a square, but you can't start with a rectangle. And so it's not always true that you can find a solution given any polygon. So given a rectangle, you can't find a solution. We're now going to look at triangle midpoints. Mary.
Suppose we have a triangle. If you see the triangle in red on the left, and if we start with that triangle, suppose given any triangle, and if the vertices of that triangle are midpoints of a bigger triangle, can we find that bigger triangle? So looking at the red triangle that we have here, can we find a bigger triangle? And so what we have on the right here is, you know, a bigger triangle. Is there more than one answer? Looking at the bigger triangle here, what do you notice? How did we come up? Already we have the bigger triangle here, but how do you think we came up with what we have on the right? Do you notice anything on how we possibly came up with that black triangle? What could we have done? What does this diagram suggest? Pam says using compasses. Great. Reminds me of construction, yes. Yeah, and what did we do with the compasses? What would your learners do with compasses in the classroom for them to come up with a black triangle?
Well, we've suggested with the words on the right, a theorem, which is taught in South Africa in, I think, grade 11, maybe grade 12. I'm not sure whether it's 11 or 12. And we'll see more about it. But what we've done is that the red triangle is joining the midpoints of the edges of the black triangle. And it should show us, we ask you what you notice. Mary's asked you, how do we find the black triangle? We know quite a lot about it. And there's some things that we might think look to be the case, like lines to parallel or triangles that are congruent. Let's go on and see
Tony,
how we discover that.
Tony Provius says using the vertex of the triangle as a midpoint to draw the line to form the big triangle.
Mm-hmm.
Yes, but that's absolutely right, Povia, but you've got to be able to, you don't know which direction those lines go in. So it's not quite as easy as your method may suggest.
Pam says use one line segment as a radius. She then says I would have to try it out.
Okay, well, it's something you can have a go at, but we're going to discuss different methods, 3 different methods of tackling it. And Caroline, what about the first method here?
Right, this one is, again, another connection with another subject matter, is using the triangle midpoints and using coordinates. So again, working with coordinates to do another task, so they're not thinking about the coordinates in of themselves. Again, 3 equations, 3 unknowns, but they're not difficult to solve because all the coefficients are 1. And you have x1 plus x2 is 2 times 7 is 14. X2 plus X3 is 2 times 6, 12. And X3 plus X1 is 2 times 8, 16.
I think the key thing here is, and I noticed that I should have put x1 plus x2 to be consistent over 2 is 7 to be consistent with what comes up below. But the thing about it is that that is a formula, and Caroline is saying that that you will be teaching, if you're teaching it, certainly if you're teaching in South Africa, and that the midpoint of an edge is given by the mean of the coordinates. The coordinates, the midpoint, are given by the mean or average of the coordinates at the endpoints. And then from that, you can turn that into 3 equations, and they're quite simple equations to solve.
Same thing as we did before. Equation 1 minus equation 2 gives you an expression with x1 and x3, and then from equations 3 and 4 you get the x is 1, x1 is 9, x2 is 5, and x3 is 7. Then use the same method to find the y coordinates, but we're not actually going to do it. If we'd had time, the idea was that you would have done both of those, but we didn't have the time. But you will certainly do that in class with your learners. Antoinette says, we'll use this in coordinate geometry, analytical geometry, she says.
Indeed, indeed. So we've covered quite a few branches of mathematics on the same theme this afternoon. So here you have got what is called the proportional intercept theorem. But in fact, and we mentioned it on a slide a couple of slides back, but this is a bit simpler than the proportional intercept because these are midpoints. And so when you join the midpoints of the edges of any triangle, the large triangle is made up of 4 congruent triangles, one of which is the triangle joining the midpoints, which you've got in red there. So what do you notice about PAB and PRQ? PAB and PRQ, focus your mind on P. And now look at PAB and PRQ. And we're going to introduce yet another branch of mathematics, if you like. It's similar triangles, but it's also an enlargement, like projecting an image on a screen with a light source at P. So the triangle PAB is enlarged by a scale factor 2 to give you PRQ. Can you see that? And similarly, if you focus on Q as, and remember, we've got ABC and we need to find PQR, but if you focus on Q, you can see that again, you've got triangle QBC and triangle QPR are similar, and you've got an enlargement with the center Q and scale factor 2, which enlarges the triangle QBC to QPR, and similarly for R.
Pam says they're similar, and that the area PQR is 4 times the area of PAB.
Well done. Yes, indeed, I agree. So now this is the proportional intercept theorem in general. If they weren't the midpoints, but there was proportionality everywhere, with similar triangles. It's called a proportional intercept theorem, but because this is a simpler version where you've got midpoints, that's what we called it in the first instance. So if you call the midpoints A, B, and C, now how would you construct it? Now you can get out your compasses or set squares, your geometry instruments, You join A, B, and C to form your triangle. That's the triangle you're given. You haven't got the black triangle yet. So the original triangle PQR can be drawn by constructing a line through A parallel to BC, and a line through B parallel to AC, and a line through C parallel to AB. And you should then be able to prove that the points A, B, and C are the midpoints of PR, PQ, and QR, using the fact that you've got similar triangles or enlargements, which is what we've just been talking about. Okay, over to you, Mary.
Pam also said that reminded her of trifold, and that she actually did that with her year 9s and they loved it.
Yeah. And just a quick one on Pam's comment about the fact that the area is ×4. I think that would be a nice way for students to see the connection between area scale factor and the linear scale factor when they're doing enlargement. It's a nice connection for learners to be able to see if they're able to identify it, or you could highlight it for them when you are doing an activity like this. So now we're still looking at triangle midpoints, but now looking at the triangle that we have, triangle ABC, that we have on the far, is it far left? Yes, we have triangle ABC on the far left. If we construct if we construct the line CP, which is, we're just taking the, if the points A, B, and C are midpoints, and we want to draw and we join them, and we have triangle ABC, and then we construct the line CP, and line CP here is the line CP, sorry, just give me a minute. Yeah, so the line CP that we have on that, on the second triangle there, if we take the midpoint of AB and we measure the distance, that distance, and then we draw line CP, which is twice that distance. So the distance from A to the midpoint of AB, and so the line CP really is twice that length. So what do you notice about the quadrilateral APBC? What can you say about the quadrilateral APBC in the very last diagram that we have on the right?
Please put your answer on the chat. And again, Pam's brought up this possibility of paper folding. And here again, you could have your ABC triangle and on a piece of paper, and you could do this by these equal lengths by paper folding. And the hint here is to prick through, so that if you're going to match A and B to find the midpoint of AB, and then you're going to find C, you've got C and you're going to find P, you would fold along the line AB, and if you've pricked through C with a pin, then that will go through the, having folded the paper, that will go through the point P. So you can either get out your rulers and compasses and set squares and things, or you can do it by paper folding. So
Patience is saying it forms a rectangle.
It looks like a rectangle, and I do agree about that. Not necessarily a rectangle, though. It's only that my triangle had an angle C looking like 90 degrees. So it turns out to be, but in a general way, it wouldn't. So Pam says it's going to be, well, Pengasi says, and other people are saying it's a parallelogram. How do you know it's a parallelogram? I agree, it is a parallelogram. How do you know?
Tony, while they're thinking about that question, if you fold on along AB, and you fold and you put a pinpoint through C, if you fold that over, it's not going to be point P.
That's absolutely
that's
true. That's true. Yes, Caroline. I take that back.
Yeah.
Yes.
But you can certainly find the midpoint. I was going to say, find the midpoint of AB by folding it.
Yes.
And then you've got that midpoint. You can then draw a line from C through the midpoint out to P, make them equidistant, and then you've got point P.
Yeah, that's true. Yes. Yes. I was over enthusiastic. Aha, now Pangesi's on the ball here. She is saying it's a parallelogram because in this quadrilateral, the diagonals bisect each other, and the diagonals of a rectangle or any parallelogram actually bisect each other equally. For any parallelogram, the diagonals bisect each other. So,
and I think maybe just to point out so that, because a rectangle is a parallelogram, but it's a special parallelogram that has right angles. So this particular one, I think it looked like the angle C especially looked like a right angle, but it's not. But yes, just so that, because some people had thought it's a rectangle because of the way it looked.
It looks like one, yes. Yeah.
This is the thing, never assume. Always, unless you actually see a right angle, you know, the symbol for a right angle on it, or you're told it's a right angle, never assume it's a right angle.
Okay.
But you carry on, Mary.
Again, sorry, just go ahead, Tony.
Oh, I was just going to say, you can, we've just done it for P, but you can carry on with the same sort of process. And you should be able to see some more. Can you see some more parallelograms there in the diagram? At the top, we've got the APBC as a parallelogram. But can you see two other parallelograms here? Look at the diagram.
See if anyone's posting just the 4 letters, just to show us which ones are the parallelograms.
I like one of them, it's crab.
CABQ, CABQ, oh crab.
CABQ is a parallelogram and the other one is CRAB, crab. Okay, let's move on. Okay, so now what we have got is a link between, this is a summary, and so what we'd like you to do is ask questions or make comments, anything you like here. And we're going to start off with a contrast here, or linking, if you like, connecting the idea of our Checkit and our Polycircles. Okay, this is just a summary of what we've learned. It's a good way to finish any workshop or lesson. What have we been doing? What's been happening? It's almost 2 hours. We've done a lot of different things. So what we did was we did some Checkit games and puzzles with 2-digit numbers, and here with 4-digit numbers. And now, again, we saw, well, we don't have to have whole numbers. We could do it with fractions, and we can do it with different operations. We could do addition, and we can do multiplication. Why not? We can be imaginative here with this Checkit, do all sorts of things. Oh, now here, we do it with exponents. So if we've got to teach exponents, this is quite a nice way to think about, and we talked about, not just finding the greatest common divisor, but also finding, and it's completely different, they're not written in the diagram there, but we could also ask for the lowest common multiple to go into the rectangles there. So there's a lovely way to give the learners some practice with exponents. Checkit exponents, we call it. And so we went on after the break. We then looked at some algebra, and here we were looking at factorizing quadratics and looking at common factors between 2 and 3 different quadratic expressions. Very important when it comes to solving quadratic equations. And we've got the difference of 2 squares at the top. We didn't mention that, but that's what we have. X squared minus 1 squared. Then we had a word game. My goodness, we have had a lot of different Checkits. A word game, and we saw there that we could be inventive. I think somebody suggested giant, which was a nice one. Okay, and that's the Checkit word puzzle. And then back to polycircles, and that was the diagram you saw earlier. And we linked that with knowing the triangle and the vertices of would be, we know they should be, the vertices of the triangle should be the centers of circles, but we just want the circles to touch each other, like Caroline showed you with a few circular things she'd found around the house. And in the picture on the slide, you saw some plates from my kitchen. Okay. And that's the activity we call polycircles. And then we went on to talk about linking up 3 points, starting with 3 points, which are the midpoints of the edges of a triangle, but we don't know what the triangle is. And can we find the triangle? So we're given the red triangle, can we find the black triangle? And we usually work these problems around from given 2 points, what is the midpoint? But now we're given the midpoint and we've got to find those 2 points at the end. And how did we do that? Do you remember? That's we call triangle midpoints. Well, we did it in different ways. One of the ways was using coordinates, sometimes called coordinate geometry and sometimes called analytic geometry. So we found the solution using coordinates. And then another solution here was using medians. That is, the medians of a triangle are the lines through a vertex and the midpoint of the opposite edge. They are medians. So we can construct the medians, and that, do you remember, that gave us 3 parallelograms, APBC, BQ, CA, and CRAB. And that shows that you've got parallel lines there. And we can have a solution using the triangle midpoint theorem. That generalizes A, B, and C don't have to be midpoints, but you can have them proportionally, and similar triangles that are, so A, B, and C are similar to triangles similar to triangle PQR, but not necessarily with the proportion being 1 to 2. And all of these geometry examples, the polycircles and the triangle midpoints, can be thought of as solving 3 equations, very simple equations in 3 unknowns, where you know what the edge lengths are, or you know something about the formula for the midpoint of a line segment. Okay,
just
so
to let you know, I've got a comment from Mogaladi, who's in my tutor group. The diagonals are equal and bisect each other. And he says there's no reason for C to be 90 degrees. There's no information on it.
I absolutely agree, Mogaladi. And in fact, had I realized, I wouldn't have made C look like 90 degrees, because that But anyway, it's led to quite an interesting discussion, hasn't
Yeah,
it?
and it's a very good, no, actually it's not a bad thing, Tony, because many questions look like 90 degrees, but they're not. So it's actually important to never ever assume that it's 90 degrees unless you're told it is or that it's indicated.
But the diagram right at the bottom of the screen there shows you that even though the quadrilateral PBCA looks like a rectangle, the other two certainly don't. They're certainly parallelograms. Okay, so I hope you'll find something interesting here that you can use with your classes in lessons, and in fact perhaps use them at different times. And they make very good lesson starters, just 5 minutes at the start of a lesson to play a game or to present it as a puzzle for everybody to solve. And then that leads on to whatever the intention for the rest of the lesson is, something on adding fractions, or on factorizing quadratic expressions, or on exponents, or on some geometry like this theorem about triangle midpoint. So if you haven't registered yourself with the GTEN, then please, a GTEN teacher, this is Global Teacher Empowerment Network, then just send on the next slide, it'll come up, send a little request to admin at aimsec.ac.za, and it'll come up in a minute, that link will come up in a minute, and ask to be put into the GTEN teachers WhatsApp. Thank you for joining us. Please use our ideas and comments and share what you've learned with other teachers on the WhatsApp page for GTEN, our WhatsApp group, and try to help all your learners to have a yes, I can positive attitude to mathematics. So goodbye from me.
Bye, everyone.
Bye everyone. Absolute pleasure. Thank you so
Bye
much for
everyone.
coming.
Bye everyone.
Thank you.
Thanks indeed.